All right, good afternoon, Professor. My name is Ming, and welcome to my video explanation for the fourth project of this course. So, the fourth project tackles the page replacement algorithm. Let me bring up the project detail before I start explaining my code. All right, project 4. The project objective is to compare the performance of page replacement algorithms for a fixed number of frames using optimal FIFO, LRU, or second chance. For the project, I'm going to be using FIFO and LRU. And my assignment is to implement the generate reference string method. And I have to generate reference strings by varying the input parameters to mimic different program behaviors. I also have to implement 2 or more page replacement algorithms. So yes, I am going to implement 2. And I have to record and plot the number of page faults generated by different algorithms. Let's move on to the code. So inside the code, I have 3 functions. One to generate reference string. Another one is the FIFO algorithm, which prints out the number of page faults. Another one is the LRU algorithm, least recently used algorithm, which also prints out the number of page faults. And it detects page fault and it deals with page fault via a queue. Down here, I have 2 helper functions: generate random number and print queue to help me with. One is to help me with generating the reference string, and the other one is to help me debug. All right, let's move on to the generate reference string function. It's a function that takes in the starting location. It doesn't. Starting location can be 0 or p. It also takes in the size of the locus, the rate of motion, the probability of a transition, the virtual memory size, and also the max reference string size that you want. Right, so how does this function work? Well, first, it gets into a while loop. It defines a reference string to store the reference string generated inside this while loop, and then it goes into the while loop. So here is the pseudocode on the right hand side. Inside the while loop, the program generates m, here you go, 0 to m, so it's m number of integers from the range s to s plus e or p minus 1. The reason why I wrote it this way is because if s is significantly large, or if e is significantly large enough to go over p, the algorithm would choose p minus 1 instead of the very large s plus e value. Then it pushes the integer into the reference string, and it checks whether if it should break out of this entire loop, the entire while loop. The condition to check if it should break out is whether reference string size is the same as the max reference string size that we set. After generating the number, after appending the number, we also generate a random double in the range 0 and 1, and we check whether the generated random double is smaller than the probability of transition. If it is smaller than the probability of transition, we generate a new location s in the range 0 and p minus 1. Otherwise, we increment s by 1 modulo p. The reason why we want modulo p is because we want it to loop backwards to 0 when s is greater than p, or when this part here goes over p. All right, now for my FIFO algorithm. So my FIFO page replacement algorithm does the FIFO page replacement. It takes in the number of physical frames, and it also takes in the reference string. It then prints out the number of page faults that occurred. So how does it work? Here is, on the right hand side, the pseudocode. So first it initializes the physical frame m, where there are f number of integers or f number of frames. It also defines the page fault counter and an oldest page index, which is usually 0. This can be set to any other page, but for the sake of this explanation, I set it to 0 because I also initialize m starting with 0. As you can see, I equal to 0 and m is initialized with 0. That's the first page that's inside the page frame, and it's also going to be the first page to be replaced. All right. So for each reference string, I find the index of the new page here inside the frame, the physical frame. If the reference string is found, then there is no page fault. But if the reference string is not found, given by this -1 here, then a page fault has occurred. When a page fault occurs, first the algorithm replaces the first page that entered m with the new page, basically the index of the oldest page with the new page here, and then it increments the index by 1 modulo f. The reason why we want modulo f is because there is a limited number of page frame. So let me draw the algorithm. Let's say page 0, 1, and 2 entered the physical frame, and there's only 3 frames available. If page 3 were to want to enter this physical frame, 0 would be removed first because it is the first to enter this physical frame. That's how FIFO works. And then the next one to be removed is 1, next one to be removed is 2, and the next one to be removed is this 3 here, every time there's a page fault. Hopefully that makes sense. I'm going to move on to the LRU in a second. Yeah, at the end here, I will print out the number of page fault and delete the dynamic array m. Now for LRU. LRU takes in the same type of parameter as FIFO. It takes in the number of frames, and it takes in the reference string. So what does it do? Well, firstly, it initialized the, look on the right-hand side for a little. This is the algorithm for LRU. It's a little bit more complicated. So first things first, it initialized the physical frame, same as FIFO. Then it defines a queue. Afterwards, it checks for each reference string. It looks for the index of the new page to check if the new page already exists in the frame, same as the previous algorithm. If the new page is not inside the frame, then a page fault has occurred. When a page fault occurred, it looks for the index of the oldest page inside the queue here. I forgot to mention that queue is also initialized. Queue is also initialized with when we initialize m in this for loop here. So let's go back to our algorithm right here. So it looks for the index of the oldest page. So from 0 to f, it checks within m if there's any page that is equal to the oldest page. If that is the case, then it sets the oldest page index as that, well, as j. I could break out of this, but since page numbers are unique inside the physical frame, I don't have to. I can let this for loop run. I can make it more efficient by breaking it out early. Then I increment the number of page fault to keep the counter. I forgot to mention in my FIFO algorithm, I also increment the number of page faults in order to count how many page fault has occurred. And then I do the replacement. I replace the page at this index with the new page. I push the new page to the queue, and then I pop the front of the queue. If a page exists inside the physical frame already, then I initialize a temporary queue in order to copy all the elements from queue here to temporary without the new page. The reason why I copy without the new page is because I want to push this new page to the back, to the far back. Pushing it to the far back makes sure that it is the newest page that has been pushed to the queue. And at the end, I also print the number of page fault. Okay, let's move to the demonstration of this program. Oh, I must have deleted this accidentally. Let's demonstrate this program. I've already compiled it. So all I have to do is to run the .exe. Oh, I forgot to mention the way I generate my reference string. So for this run here, the reference string mimics something called high locality, meaning there's a lot of program running, a lot of different types of program running in the system. To mimic high locality, I can increase the probability of transition and the size of the locus. When locality is really high, you can see that the LRU algorithm is performing worse than the FIFO algorithm. Right, let's reduce the locality to low. Okay, now for low locality, I can change this to 3 and 0.1. This is extremely low. Then I have to regenerate the, I have to recompile the code. Okay, number of page fault is the same. Try again. Same. So extremely low locality for the reference string here makes the algorithm work about the same pace. What happens if I make it as close as possible to how a normal system runs? And as you can see, the LRU is much faster, or it's better at replacing the pages than the FIFO algorithm. So for high locality, we see that the LRU gets outperformed by FIFO. For low locality, we see that the both algorithms perform the same, performed similarly. And for a medium or normal locality, we see that LRU outperforms FIFO. All right, that is it for my video explanation. Uh, hopefully you got all of that, and I will see you in the next project. Goodbye.